So here in example 4, we're kind of bringing the whole business side of things. We want to find the break-even point when the cost function c of x is equal to 5x plus 10,000 and the revenue function r of x equals 15x. Okay, so step 1 that we did in the prior example is we made sure both of them were solved for y. Well, if you look at this closely, we actually have that. Because remember, the function notations right here, those are just fancy for y's. It's saying y is equal to 5x plus 10,000, and then it says y equals 15x. The reason why we have the c of x there is just a way to name it, remember? And r of x is a way to name the other one. So really we're all set, ready to go to start solving this one because we have y equals this thing and y equals that, so we can start by setting that equal. So 5x plus 10,000 is equal to 15x. And remember, by definition, break-even point in business terms is when your cost equals your revenue. Well, c of x is 5x plus 10,000 and r of x is 15x, so just another way of looking at it. All right, let's finish solving this out. So let's bring maybe that 5x over. We get 10,000 is equal to 15 minus 5 is 10x. Divide through by 10, and we get x to be 1,000. Okay, so now that we have the x value, let's go back in and get the y value. And it really doesn't matter where I plug it into, either equation, since let's show it both. Let's find the cost when 1,000 items are produced, and let's find the revenue when 1,000 items are produced. Okay, the cost at 1,000 would be 5 times 1,000 plus 10,000. So 5,000 plus 10,000 is 15,000. And if I go the revenue equation, it's just 15 times my x value. So 15 times 1,000 is 15,000. So right there, it is showing you why we're breaking even, because the cost is equaling the revenue. So if I really wanted to answer this question in a full sentence, I would say basically when 1,000 units are, let's see, sold or purchased, the company breaks even. And if even after that you can say it breaks even specifically when the revenue and cost are both $15,000. Or you can say at, if you want to, at $15,000. Okay, let's go on to the next example. It looks like it's going to be number 5, which is 25 in the book on page 117. So if you'll pause the video for just 1 second, let's grab our books, read through the problem, and let's join right back in right here. Okay, so just looking at this problem, it's all about linear depreciation. And for a lot of you guys, as you're getting to your first business class, like specifically your accounting class, they're going to be talking to you a lot about depreciation, because obviously what that means, and you all have all heard about it in the real world. If you own a car, what's the first thing that happens as soon as you get off that lot and you drive the car off the lot? It depreciates in value significantly. Okay, there are things that appreciate in value. Usually land will. The longer you own your land, the value of that land might go up, which is a great thing. And then, but some things depreciate in value, and those are things like computers, office supplies, cars, equipment, things like that. They're always going to depreciate in value. So what we're doing here with this example is we're specifically looking at an office building. It was worth $1 million back in 2005 when it was being completed, but it's going to be depreciated linearly over 50 years. So basically, to an accountant, we need to look at it in this form as for the assets for this company. The assets aren't going to be the same every year. It's actually the assets are going to go down specifically towards the cost of this building. Okay, and what we need to do is find the book value of the building in 2010 and 2015. Okay. So let's think about this. I'm going to go about it. And y'all, obviously there's a fast way to do it. It's pretty simple, but I'm going to go about it kind of more of a mathematical way, so you can see the methods on how to do it every single time in case sometimes it's not so obvious. Okay, so whenever we want to look at this, we know if I wanted to look at a graph, basically, we have a dependent variable. The value of that building, which is the y value, depends on how old it is. It depends on the time. Okay, so basically, at year 0, the building is worth up here at $1 million. Okay, and then what we know is after 50 years, the building is worth $0. So it goes from worth at 2005, which is at brand new at year 0, we're worth up here at $1 million. but by the time I've gone 50 years later, my value of that building has gone down. And this is what the problem, basically the title says, it's linear depreciation. As I'm going down, I'm not going down by a curve, I'm going down by a straight line, by a linear. Okay, it's going to be linear depreciation. So let's write first of all, let's write an equation. Well, I've got 2 points here. I've got the point of when my time is 0 or my x-axis is 0, I have a value of $1 million. Okay, so there's one coordinate. I have another coordinate. 50 years later, my value is worth $0. Okay, so if I have 2 points, can I find a slope through it? Of course. The slope is just the difference in the y values. So I'm just going to go the top number minus the lower number over the top minus the lower. So if I look at basically $1 million divided by negative 50, then I have a slope of negative 20,000. Okay, and if I asked you to write this in a fraction, you would say negative 20,000 over 1. So what this represents, remember the top number is the change in your y's, is the difference in your y's, and what does the y-axis represent? The y-axis would represent dollars. The bottom is the change in the x's, it's your horizontal. So specifically the horizontal in this case is time in years. So in 1 year. What this is, if I wanted to write this out in a sentence, what we just found out is the building loses $20,000 in value each year. Okay, and that's what we just found out. So now let's go through and answer the questions. The first question it says is, what is the value of the building in 2010? So I can say the value, well, let's write ourselves an equation, a value equation. So the value of the building at time t is always going to be, it's y equals m. So m is our slope, which we found was 20,000, negative 20,000. X, which our x in this case is t, so our x-axis is time, and then plus my y-intercept. Well, what was that y-intercept? It was that initial value. It's plus 1 million. So here is our basic foundational equation right there. It's the fact that the value, and I just put v, so the value of the building at any time t is going to equal negative 20,000 t plus 1 million. Let's check it out real quick. Let's try our points. When t was 0, so right there, when t was 0, when the building was brand new, it wipes that whole front term out and you get 1 million. That makes sense because when t was 0, it was $1 million. However, if I put 50 in, well, 50 times a negative 20,000 is a negative 1 million. So a negative 1 million plus 1 million would give you a value of 0, which describes the x-intercept. Okay, so now we can take this and answer the question. It says, what's the building value in 2010? So in 2010, what is our t value? Well, t is 0 at 2005, so in 2010, we're just 5 years later. So t equals 5 at 2010. So it's going to be negative 20,000 times 5 plus 1 million. Okay, so when we do the math on this, so the value 5 years later is simply $900,000. Okay, the next part they say is, what is the value in 2015? So in 2015, then we've gone 10 years past 2005. So V of 10 is going to be a negative 20,000 times 10 plus 1 million. And doing the math on that one, we'll find the value 10 years later to be $800,000. Okay, so the most important thing I really want you all to get out of this problem is this main equation I built right there. Is the fact of what we did is we kind of formulated a couple points, we found our slope, and then we just wrote out our main equation using the y-intercept, which happened to be one of the values they gave us, and it's just y equals mx plus b. Okay. All right, let's try the next problem, which is number 28 in the book. And just reading through this problem real quick. It basically says AutoTime is a manufacturer of 24-hour variable timers. has a monthly fixed cost of $48,000 and a production cost of $8 for each timer manufactured. The timers sell for $14 each. Okay, so we've done something very, very similar to this. First of all, what is the cost function? Okay, well, let's define our variable first of all. X is going to be the number of timers produced. I need to know that because right here, if I go C of, it's like, what variable do I want to put in that? Well, let's put our variable that we want to describe, which is the number of timers produced. So the cost function is always a blend of fixed and variable. So the fixed cost, it says up there for us, is already given. It's $48,000. And then it says a production cost of $8 per timer manufactured, so plus 8x. Okay, part B says, what is the revenue function? Well, the revenue is always according to how much money they bring in whenever they sell one item. So the timers sell for $14 each, so therefore the revenue is 14x. The cost function is always, the profit is always revenue minus costs. So in this case, it's 14x minus, and again, I'm putting two terms, the 48,000 and the 8x behind a minus sign, so I've got to make sure I put it in parentheses. So 14 minus 8 is 6x minus 48,000. Okay, so hopefully y'all are getting really familiar with this. And now, last but not least, what they want us to do is find, for part D, we want to either find the profit, which is a loss, or an actual gain of production levels of 4,000, 6,000, and 10,000. So let's just do a few of these. How about, let's just do the profit at 4,000, because y'all are hopefully getting a good idea of this, and the profit at 10,000. Okay, so the profit at $4,000 would be 6 times 4,000 minus 48,000. So if we have 24,000 minus 48,000, then it's a negative 24,000. Ooh, that doesn't look so good, does it? So what that definitely means is they did not make a profit. You do not want to sell, this company does not want to sell only 4,000 timers. It needs to sell a lot more than just 4,000 timers in order to go, break even or make a profit. Okay, and then at 10,000, we have 6 times 10,000 minus 48,000. So 60,000 minus 48,000 is 12,000. So obviously a much better number. So we make a profit, we go in the green when we sell 10,000 timers. We definitely go in the red whenever we sell 4,000 because now we're definitely in the hole. Okay, let's go on to example number 7.